Previously, we have introduced the Layer 2 Ethernet switching and the basic concepts and configurations of VLAN and trunking. In today's course, we will go through how to implement inter-VLAN routing. We'll first look at the inter-VLAN communication mechanism and learn how to implement inter-VLAN routing through sub-interfaces. Then, we will talk about the working mechanism of Layer 3 switches and learn how to implement inter-VLAN routing through VLANIF interfaces on Layer 3 switches. First, let's look at how to implement inter-VLAN routing through sub-interfaces. Let's recap what we have learned about Layer 2 Ethernet switching. VLAN is a basic concept of Layer 2 switches. A VLAN is a logical subnet or a broadcast domain. Different VLANs are different broadcast domains and therefore are isolated on the switch. If two network elements connecting to the same switch belong to different VLANs, they cannot directly communicate. This is Layer 2 isolation. Why do we need VLANs? A switch is a broadcast domain. As a network expands, more and more switches and network elements are deployed, and the broadcast domain is enlarged. Once a broadcast storm occurs, the network will be heavily burdened. To minimize the impact of broadcast storms, we need to design smaller broadcast domains to limit broadcast packets within smaller scopes. As previously mentioned, a VLAN is a logical subnet or a broadcast domain, and traffic between different VLANs is isolated on the switch. In live network scenarios, enterprises generally have multiple VLANs deployed for isolating broadcast domains. For example, an enterprise has two departments, Department 1 and Department 2, belonging to VLAN 10 and VLAN 20 respectively. PCs from the two departments need to communicate with each other. However, because the two departments belong to different VLANs, their PCs cannot communicate at Layer 2. Because PCs in different VLANs cannot communicate at Layer 2, they have to communicate at Layer 3. This communication requires a Layer 3 device. The earliest way to implement inter-VLAN communication is through a router. In this example, the switch connects to VLAN 10 and VLAN 20. PC 1 belongs to VLAN 10. Its network segment address is 192.168.10.0. IP address is 192.168.10.1/24, and gateway address is 192.168.10.254. PC2 belongs to VLAN 20. Its network segment address is 192.168.20.0. IP address is 192.168.20.1/24, and gateway address is 192.168.20.254. PC1 connects to GE0/0/1, and PC2 connects to GE0/0/2 on the switch. These interfaces are configured as access interfaces and added to VLAN 10 and VLAN 20 respectively. Because PC1 and PC2 are isolated by the switch, they cannot communicate at Layer 2. We can add a router to this networking. The router uses two physical interfaces, GE0/0/1 and GE0/0/2 to connect to two different network segments. Specifically, the router's GE0/0/1 connects to the switch's GE0/0/23, and the router's GE0/0/2 connects to the switch's GE0/0/24. Then a complete topology is formed. To allow PC1 and PC2 to communicate, configure the switches GE0/0/1 and GE0/0/23 as access interfaces, and add them to VLAN 10. The link in red is used for VLAN 10. Similarly, configure the switches GE0/0/2 and GE0/0/24 as access interfaces, and add them to VLAN 20. The link in blue is used for VLAN 20. On the router, configure GE0/0/1 as the gateway for VLAN 10, and assign IP address 192.168.10.254 to GE0/0/1. Configure GE0/0/2 as the gateway for VLAN 20, and assign IP address 192.168.20.254 to GE0/0/2. After the configurations are complete, network communication is enabled. When PC1 wants to communicate with PC2, it sends a data frame to the switch. Because the switches GE0/0/1 and GE0/0/23 are both access interfaces and belong to VLAN 10, they transparently transmit the data frame to the gateway of VLAN 10. After the router receives the data frame from its GE0/0/1, it finds that the destination IP address in the Layer 3 IP header of the data frame is 192.168.20.1. The router then looks up the routing table to find that it is directly connected to network segment 192.168.20.0, which is exactly where its GE0/0/2 resides. Therefore, the router routes the data frame out through its GE0/0/2. The data frame then goes through the switch and finally reaches PC2. This process is called inter-VLAN communication, or Layer 3 communication. This method is direct and easy to configure, but does it have any weak points? In this example, the switch isolates two VLANs, so the router must provide two physical interfaces to connect the two VLANs. If there are 10 VLANs, the router must provide 10 physical interfaces. We know that switches generally have 24 or 48 interfaces, but routers have far less interfaces. As such, this method is not scalable and is inapplicable to large-scale networks. What can we do about it? Will it work if the router provides only one physical interface for more than one VLAN? The solution is something called sub-interfaces. Sub-interfaces are also called one-armed routes. In the previous example, the router used two physical interfaces to connect to two VLANs. In this topology, the router provides only one physical interface, and so does the switch. Therefore, the switch and the router can be connected through only one physical link. How does one physical link carry traffic from two VLANs? It works as if there is a big pipe containing two small pipes for each VLAN. and each small pipe is a sub-interface. Sub-interfaces are important in many scenarios. First, a sub-interface is configured on the physical interface. For example, if you configure a sub-interface for GE0/0/1, then the sub-interface can be GE0/0/1.x, x being any digit. Second, a sub-interface is a software-based logical interface. It does not physically exist. Third, a sub-interface can have an IP address configured and is a Layer 3 interface. One sub-interface serves only one VLAN, and you must also specify a VLAN ID for the sub-interface. Note that no configuration is needed on the physical interface when you configure a sub-interface. All you have to do is to ensure that the physical interface is enabled. After a sub-interface is created, you can configure an IP address and a VLAN ID for the sub-interface. The switch's interfaces connecting to VLAN 10 and VLAN 20 are access interfaces, and the interface connecting to the router is a trunk interface for carrying traffic from the two VLANs. The trunk interface must be configured to allow packets from VLAN 10 and VLAN 20 to pass through. The router has two sub-interfaces configured, GE0/0/1.10 and GE0/0/1.20. The IP addresses of the two sub-interfaces are 192.168.10.254 and 192.168.20.254, which are exactly the gateway addresses for VLAN 10 and VLAN 20. Let's see how we create sub-interfaces. In this topology, the switches GE0/0/1 and GE0/0/2 connect to PC1 and PC2 respectively. They are both access interfaces. GE0/0/1 belongs to VLAN 10 and GE0/0/2 belongs to VLAN 20. The switch uses a trunk interface to connect to the router. The router's GE0/0/0 is enabled. Now we have to create two sub-interfaces, GE0/0/0.10 and GE0/0/0.20 on GE0/0/0. Run the interface gigabit Ethernet 0/0/0.10 command to configure GE0/0/0.10. Run the .1q termination vid10 command to add GE0/0/0.10 to VLAN 10. Run the IP address 192.168.10.254.24 command to configure IP address 192.168.10.254/24 for GE0/0/0.10. The ARP broadcast enable command is optional. The configurations for GE0/0/0.20 are similar. When PC1 wants to communicate with PC2, it sends an Ethernet data frame to the switch. Upon receipt of the data frame, the switch adds a VLAN tag with the ID of 10 to the data frame, and then sends it out through the trunk. After the router's GE0/0/0 receives the VLAN tagged data frame, it finds that the data frame is tagged with VLAN 10. Therefore, the router's GE0/0/0 removes the VLAN tag with the ID of 10 and sends the data frame to GE0/0/0.10 corresponding to VLAN 10. GE0/0/0.10 finds that the destination IP address in the data frame is 192.168.20.1/24, and the network segment is where GE0/0/0.20 resides. Therefore, GE0/0/0.10 sends the data frame to GE0/0/0.20. GE0/0/0.20 adds a VLAN tag with the ID of 20 to the data frame and sends it out to the switch. After the switch receives the data frame, it removes the VLAN tag with the ID of 20 and sends it to PC2. This is how inter-VLAN communication is implemented through sub-interfaces. Using sub-interfaces to implement inter-VLAN communication, however, also have weak points. When PC1 and PC2 are communicating with each other, data is transmitted twice through the link between the switch and router, causing high loads on this link. This may even lead to a network bottleneck. In application and software networking scenarios, a firewall is used instead of a router, and multiple physical links exist between the firewall and switch. These physical links can be bundled into a logical link, called an ETH-trunk link. Sub-interfaces can then be created on the ETH-trunk interface. The use of ETH-trunk interfaces improves link bandwidth. Let's have a quick recap. A router uses a physical interface to connect to a downstream switch. The switch uses two access interfaces to connect to PC1 and PC2. The router performs routing, and the switch performs layer 2 switching. When traffic travels from PC1 to PC2, it must go through the switch and then the router. Why can't we integrate the routing function into the switch? A layer 3 switch is capable of doing this. This is a layer 2 switch chassis with a layer 2 switching module. The 4 interfaces on the switching module are access interfaces. Those belonging to VLAN 10 are marked pink, and those belonging to VLAN 20 are marked blue. In this layer 3 switch, there is also a routing module. The routing module has VLANIF interfaces configured for specific VLANs. VLANIF interfaces are sometimes called Switched Virtual Interfaces, SVIs. After a VLAN is created, you can create a VLANIF interface. For example, after VLAN 10 is created, you can create the VLANIF 10 interface. VLANIF interfaces are also layer 3 sub-interfaces, but they are created on the routing module of the layer 3 switch. VLANIF interfaces correspond to VLANs and perform layer 3 routing for VLANs. We can run the interface VLANIF 10 command to create the VLANIF 10 interface and run the interface VLANIF 20 command to create the VLANIF 20 interface. After VLANIF interfaces are created, you can configure IP addresses for them. The IP addresses of VLANIF interfaces serve as the gateway addresses for VLANs. For example, the gateway address for VLAN 10 is the IP address of VLANIF 10 interface, and the gateway address for VLAN 20 is the IP address of the VLANIF 20 interface. When PCs in VLAN 10 and VLAN 20 need to communicate, traffic from a PC in VLAN 10 first arrives at the switch. The access interface receiving the traffic performs layer 2 switching and sends the traffic to the VLANIF 10 interface. Next, the VLANIF 10 interface performs Layer 3 routing and sends the traffic to the VLANIF 20 interface. The VLANIF 20 interface then sends the traffic to the access interface connecting to the PC in VLAN 20 at layer 2. Next, let's look at the basic configurations of VLANIF interfaces. Let's take a simple network as an example. A layer 2 switch is connected to two PCs. PC 1 belongs to VLAN 10 and PC 2 belongs to VLAN 20. The gateway address of VLAN 10 is 192.168.10.254, and that of VLAN 20 is 192.168.20.254. It is required that PC 1 and PC 2 communicate with each other. First, we configure the layer 2 switch. Run the VLAN batch 1020 command to create VLAN 10 and VLAN 20. Add GE 0/0/1 to VLAN 10 and GE 0/0/2 to VLAN 20. Specifically, run the interface gigabit to Ethernet 0/0/1 command to create GE 0/0/1 and enter its view. Run the port link type access command to configure GE 0/0/1 as an access interface, and run the port default VLAN 10 command to add GE 0/0/1 to VLAN 10. Then repeat these steps to add GE 0/0/2 to VLAN 20. So far, layer 2 configurations on the switch are complete. Next, we will perform layer 3 configurations on the switch. Configure VLANIF interfaces and assign IP addresses to the VLANIF interfaces so that they can serve as the gateways for the VLANs. Specifically, run the interface VLANIF 10 command to create the VLANIF 10 interface and enter its view. Run the IP address 192.168.10.254.24 command to assign an IP address to the VLANIF 10 interface. Then repeat these two steps to create the VLANIF 20 interface and assign an IP address to it. After these configurations are complete, PC 1 and PC 2 can communicate through the VLANIF interfaces. Let's summarize what we have learned using this networking with a layer 2 switch, a layer 3 switch, and a router. PC 1 belongs to VLAN 10 and PC 2 belongs to VLAN 20. SW1 is a layer 2 access switch that connects to PC 1 and PC 2 in different VLANs. SW2 is a core switch. The gateways for the two VLANs reside on SW2. SW2 uses the IP address 192.168.99.1/24 to communicate with the router with the IP address 192.168.99.2/24 through VLAN 99 on the network segment 192.168.99.0. It is required that PC 1 and PC 2 be able to communicate with each other and successfully ping the router. The gateway address of PC 1 is 192.168.10.254/24, which is the IP address of SW2's VLANIF 10 interface. The gateway address of PC 2 is 192.168.20.254/24, which is the IP address of SW2's VLANIF 20 interface. Because both gateways reside on SW2, the link between SW1 and SW2 must carry layer 2 traffic from both VLAN 10 and VLAN 20. As such, This link must be configured as a trunk link and to allow traffic from both VLAN 10 and VLAN 20 to pass through. SW2 needs to communicate with the router through VLAN 99 because interfaces on switches cannot have IP addresses. SW2's GE0/0/24 must be added to VLAN 99 and configured as an access interface. The VLANIF 99 interface must be configured and assigned IP address 192.168.99.1/24. SW1, SW2, and the router must be configured. Remember that the routes destined for return traffic must be configured on the router. In actual applications, a default route must also be configured on the core switch SW2. The networking we just described can be displayed by this logical diagram. Interfaces marked yellow, green, and blue in solid lines are access interfaces and belong to VLAN 10, VLAN 20, and VLAN 99, respectively. The interfaces in gray are trunk interfaces. The interfaces circled with dotted lines are VLANIF interfaces. When PC1 and PC2 communicate, traffic goes this way. When PC1 communicates with the router, traffic goes this way instead. In today's course, we talked about the implementation of inter-VLAN routing through sub-interfaces and VLANIF interfaces. These are the detailed configurations for your reference. That's all for today. Thanks for listening.